Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
Hold on,
everybody. Get situated. Get ready. Producer Watson, are we ready to go?
What does Watson say?
He goes, He's ready to go. No, he's tuckered, man. He's tuckered. We're doing this late night record sesh here, and he's like, dude, it's time for bed. What are we not doing in bed right now? This isn't office time. This is go to bed
You
time.
are not an early to bed kind of guy, though.
No, that's true. I'm not. Neither are you, really.
And you are a very... no, I'm not. But you are an early riser.
You are an early to fall asleep on the couch with Doritos in your hand guy.
Absolutely.
Chris doesn't go to bed early.
Chip.
He goes to sleep early, but not to bed.
Yeah, I do. Best chip ever made, Doritos. They are. It's hands down. It's not even a question.
Oh, so good.
Me and processed cheese get along very well.
Very well. You're just besties. BFFs,
I am.
man.
We are.
That's good stuff.
Well, hey, Jesse, this is part 2 of Earth's oldest rocks, of the Acasta Gneiss specifically, right?
Yeah, this is part 2. And we are, this is where, Chris, you're going to have your work cut out for you, getting me out of the weeds. Because okay, here's the setting. We got asked a listener question a while back from Mark, who asked us about the Acasta Gneiss specifically, which sent off alarm bells for
thanks,
me.
Mark.
Because, yeah, thanks, Mark. Because this is home turf. This is, this is where I did my PhD. But this kind of got expanded, Chris, into a series of podcast episodes on Earth's oldest rocks that also we've combined with images and are available as an audiobook on the Camp Geo mobile app, which is the first link in your show notes where you can go. You can find a ton of free content, and also Geology of Yellowstone, Geology of the Grand Canyon, Geology of the Grand Tetons, and a book on Earth's oldest rocks, which I don't know, Chris, when we're talking about rocks specifically, the images do a lot. The images actually add a lot of value, I think. So go there, you'll get some extra content with images.
Of course they do. That's the hope, right?
That's the hope, right?
Look, that's why I fell in love with geology, actually. I fell in love with geology through imagery and videography. I wasn't in the field. The field sealed the deal, right? But it's a visual science.
It is. And to do it well, the podcast, we do a good job, I think, of explaining these topics in audio, but there's some things you just can't get across in audio. So you can go to our Camp Geo app and get this podcast content with images in the Earth's Oldest Rock chapter. But the point is, this has expanded into a series on Earth's oldest rocks, kind of because it's home turf for me. And Chris, our last episode, part 1, was basically the history of the discovery of the Acasta Gneiss complex, the science up until around about 2010, which is when I started my PhD work.
There was a time, Jesse, when you would not shut up about the Acasta Gneiss. And so me and Andy and other people that you're acquainted with
Mike
would just
Ackerson,
refer to you as Acasta.
Yeah, friends of the pod refer to me as...
Oh my gosh, shut up, Acasta. Okay, we've heard enough.
This is probably... Every PhD student goes through this. I had an extended period of time in the wouldn't shut up about his project time period where it's like, dude,
it's understandable, but that doesn't mean we're going to let you get away with it.
No, of course not. No.
I get it, but I'm still going to rip on you about it. But
wouldn't expect
Jesse,
you to.
So that's where we came from, setting the stage for the history of the Acasta complex. Now, you have looked into the petrology of rock samples, and you've actually come up with kind of a different, how do I say this? You've framed this maybe in a different tectonic setting, if you will. Is that fair? You kind of are thinking more along the lines of this Icelandic setting, where you have layer upon layer upon layer of igneous rocks. And when you layer this volume of rocks, the geothermal gradient comes into play, and you have heat and you have pressure and metamorphism then invariably.
Yeah, exactly. Does a lot of melting. And so, Chris, let me just back up just slightly and give kind of the perspective what my PhD contributed as new to the understanding of the Acasta Gneiss complex. So at the time I started, The rocks had been discovered. They had been dated pretty well, and people had mapped them. Sort of, we had talked about finding these really high-strained flaggy gneisses, the lower strain zones, which are still gneisses and pretty deformed, but not quite stretched into oblivion. My contribution, I would say, during my PhD was we had found, kind of by sheer luck, a part of the area that was actually much less deformed and preserved pretty decent rock compositions. The minerals were still sort of recrystallized, but we would believe the chemistry of these rocks. Like if I took a sample, I would believe that the chemical composition of that rock matched pretty closely the original magma's chemical composition, which means we could do what, quote unquote, petrology. We could understand the genesis of the rock. Whereas those flaggy gneisses...
Hold on. I'm sorry. I just want to back up for the listener so we understand. What you're saying is the chemical composition of the metamorphic rock very closely matched the chemical composition of the igneous rock, which was the protolith, the parent rock.
That's
right?
Exactly right, Chris.
So the magma cooled and crystallized into the igneous rock. The igneous rock was tortured into a metamorphic rock, but there was not a dramatic change in chemistry that took place.
Exactly right. There wasn't like massive overprinting.
You have a lot of fluids involved and things like this that are bringing things in from
rock
elsewhere.
Types together. Like it's a meaningless number when you're mixing rocks, whereas we found an area that preserved pretty good rocks. So we could do petrology really on these rocks for the first time. And what we found for especially the oldest rocks.
Hold on. But I'm sorry. I hate to do this because I really don't want to interrupt your flow. But you said by luck. What does that mean? You found this by luck.
Well, it's a combination of luck and just spending time walking around in the rocks. But we found an area that preserved. Well, what happened is that my PhD supervisor had gone up there on a
Chaco.
A couple years before on a field trip with undergrads, like an undergrad mapping exercise. They'd gone to the Acasta Gneiss complex. He'd kind of rocked up to an outcrop. One of his students had gone up and sort of just took a random sample and brought it back to the lab, and they dated it, and it had spectacularly preserved zircons that were 4.02. So he's like, oh, wow, we randomly grabbed the oldest rock in the Acasta Gneiss complex. We knew that they're around. We just didn't know that this was one of them. So I went back, building on that. I started in a master's project, and we went up there, we sampled it, we poked around, we looked at the outcrops. We're like, wait, this is actually kind of a nice package. It's a nicely preserved kind of package of rocks that we could probably do some stuff with. And that led to a PhD.
So just to be clear, you found the rocks and you didn't like pick up the rock and know, oh, we found a rock that had 4.02 billion year old zircon crystals in it. This meant that you picked up the rocks, you did all of the things to establish the location and the orientation of the rocks and so on that you took them from, and then they were in the lab. So this was a months-long process, and you're like, oh my gosh, we found the oldest rocks. We just happened to find them, right? So then you came back the next year, right? So just sorry, I want to make sure that everyone's following that.
This is a great point, and we're going to come back to this point because working in these types of really complicated, multiply deformed, tortured rocks, it requires this iterative process. It requires you to go in the field, collect samples, make a map, come back, date them all, do the random geochronology and zircons, then think, okay, wait, my map was wrong there because the numbers are telling me that, so I got to go back and rethink it. And I did this 3 or 4 years during the course of my PhD, this kind of go up every summer and refine it kind of thing.
So real quick, Jesse, so you said that this was more of an Icelandic setting as opposed to a subduction zone setting. So talk about that. What led you down the path that these regionally metamorphosed rocks didn't have anything to do with subduction zones?
So in a subduction zone, the magmas that are formed in a subduction zone, think of the Sierra Nevadas, think of Yosemite National Park. Those rocks were formed above a subduction zone system. The chemistry of the rocks, the chemistry of the granites, record key signatures that tell you this was formed in a subduction zone system. In subduction zone, magma formation is deep and it's wet because the slab going down brings water down into the mantle. That melts really deep and it forms magmas that are deep and wet. And you can see various chemical signatures that tell you deep plus wet. What we saw when we looked at especially the oldest rocks in Acasta, the 4 billion years and the 3.9 billion year old rocks, was not a deep wet signal. We saw a shallow dry signal, which is very much more a mantle plume kind of a signal. They match chemical compositions to a really rare suite of rocks called Icelandites that occur only on Iceland.
Okay.
And so the chemistry just kind of matched the chemical fingerprint. We talked about this a bunch in our like Yellowstone geology book, Chris.
Yeah,
like
we did, but not
yeah.
really in this terminology. And you need to, like, you're skipping some steps here in terms of it gives you a shallow, dry signature, if you will. All right, you need to explain, like, what does that mean? What is that signature and how do you recognize it?
Okay. The signature, what the chemical signature is it's iron enriched, is what we call iron enrichment trend, or some people call it tholeiitic. You might have heard tholeiitic trend versus calc-alkaline trend. Calc-alkaline means calcium, and the alkalis, potassium and sodium, are enriched, whereas the iron enrichment trend, or tholeiitic, means there's a lot of iron in these rocks. So if you compare rocks, so magmas differentiate. We've talked about this. We talked about this in the Camp Geo chapter. We have some great images on differentiation, but magmas go from mafic to felsic. They kind of evolve. As they evolve from mafic to felsic, they're increasing the silica content of the rock. The other elements are changing as well. Iron, potassium, sodium, those are changing as well, but they don't necessarily always change in line with silica. And so in Iceland, in a place like Iceland, we have this what's called an iron enrichment trend, where iron gets really high really fast. And then in a subduction zone system, the iron kind of stays in line with silica. It kind of drops as silica increases. So the two very different trajectories when you compare iron to silica in these rocks. And the cause, so that's the signal. The cause is everything to do with plagioclase. Plagioclase, the mineral plagioclase, is stable when magmas are shallow and don't have a lot of water in them. And so in Iceland, what controls this iron enrichment trend is that the magma, let's say basaltic magma, injects itself into the crust and sits there and cools down. It's shallow and it's dry, so plagioclase will be stable. And plagioclase forms and fractionates out. It crystallizes out, which plagioclase removes calcium, aluminum, silica. It removes it out of the magma. And what it doesn't remove is iron. And iron gets driven up really fast in the magma itself. Now, we'll compare that to a subduction zone setting where a magma intrudes really deep and it's wet. It's wet and it's deep. That magma, plagioclase is not stable. So you'll crystallize clinopyroxene and olivine, and the iron will get soaked out of that. It won't end up in the magma. The iron will get drawn out and crystallized down, and then the stuff that erupts on the surface doesn't have a lot of iron in it. So it's really about plagioclase, whether plagioclase is stable, and that's shallow dry. Plagioclase is stable and shallow dry, if that makes sense. So this gets into like advanced
complicated
level petrology.
geochemistry.
Yeah,
absolutely.
exactly.
Yep.
But that's the signal we sort of see that makes us think it's an Iceland-like kind of setting.
So Iceland can be thought of kind of like a layered cake then, right? Where the composition changes. So what you're saying is toward the surface, it's more iron enriched. Is that correct? Am I getting you?
Broadly, yes. When you have, Iceland also erupts a ton of basalt too. So you get this layer of basalt on top.
This is, if you have these different layers, it can explain how Iceland has really vastly different kinds of eruptions that happen. Some violent and some non-violent.
Absolutely. So there's two different ways that felsic rocks are really formed on Iceland. One is by this extreme differentiation, extreme fractionation. The other one is Iceland erupts a ton of basalt. That basalt gets hydrated, water interacts with it, and then it gets buried by later basalt. And it gets buried such that it gets melted. So the rhyolites in Iceland are often formed by that melting of the basalt as it kind of gets buried and buried and buried, and it's wet and it's sopping wet and it gets melted. The Icelandites are formed by this extreme fractionation. So put a basalt there and crystallize 80% of it or 90% of it. That last 10 or 20% is going to be Icelandite composition, this iron enriched rock, which we see in Acasta. So at risk of sort of belaboring the point there, like that's what we contributed, I think, in my PhD, was this sort of thinking about the chemistry of these magmas because we found this nice area. At the same time, Annie Bauer, who's now a professor at University of Wisconsin, was doing her PhD with Sam Bowering, actually, on samples from the Acasta Gneiss complex. She came into the field with us, and she was working on the isotope geochemistry, and she started seeing signatures that Acasta, the rocks that we see in Acasta, she was kind of confirming some of these signatures and observing new ones, that the 4 billion and the 3.9 billion year old rocks were actually formed, their source material, what melted to form those, was 4.3 billion years old. So there's like even older crust that was melted to form the rocks we see today.
Now, is that a new technique that allows a researcher to go back to that?
It's so like Chris, we talked about this in a previous episode about like how the earth I forget it was how the earth works or something like that.
We forget things, don't we?
Chris has forgotten more than most of us have learned in our lifetimes.
That's true. It's sadly true. It's so depressing. Yes.
But we talked about neodymium. We talked about the extinct neodymium isotope and how it can be like a tracer. So if you see a lot of this 142 neodymium or 143 neodymium in the rock, it had to come from something that had a lot of samarium in it, and that's felsic crust, right? So that kind of tells you, did it come from the mantle or from a crustal composition? And so those are the types of techniques that Annie was using to analyze these rocks.
How long did that process take? Was this like she was doing her PhD at the time, so was this like a 4-year project?
Yeah, this is a solid PhD project. Yeah.
Okay. All right, Jesse, it occurs to me that we never really set the stage for where Acasta is.
Oh, yeah.
We should have done that right at the outset.
We definitely should have done that. So we do have a Google Earth image. We just
referred to it as a craton, okay, it's in the craton, but be specific.
Okay, go, if you're in the U.S., let's go from there. You go to the Montana border, Montana-Alberta border there, and you got to drive, basically to drive straight north all the way to the top of Alberta, it's like a 12-hour drive. No, it's more than that. 16-hour drive. Then you hit the Northwest Territories. You got to drive up to Yellowknife. Yellowknife is where the road ends. There's no real all-season road that goes north from Yellowknife, really. There you take a float plane from Yellowknife about 200 miles north to the Acasta Gneiss complex, and there's a beautiful little beach landing area you land on, and there's a little island that everybody camps on in this Acasta River system. I mean, it's the Canadian Shield, so there's like 40% water and 60% rock.
Okay, so to summarize, this is a long ways north. It's in the Northwest Territories, and it is not easy to get to.
It's not easy, and this is why it's not well studied, is because it's so remote. So it takes a long time to get there. Okay,
so Jesse, let's do this part of it really quickly, but what are some other people maybe have worked on regarding the Acasta?
So there's a bunch, and I'm going to be, this is my podcast, so.
Yeah, hey, what did you just say?
I said this is my podcast, so I get to say what I want.
Oh my gosh, that hurt my heart, Jesse. You just took over right now.
Well, I've been slowly taking over by, not allowing you to hit the record button in the new software
not letting
we use.
Me get a word in edgewise either. So holy cow.
Picking topics that
it's time to
I just talk and talk and talk and
talk
about.
All right. So one of the research groups they've zeroed in on meteorite impacts as maybe the source of the Acasta Gneiss, right? What do you think?
I think it's a more complicated model, and not necessarily, we don't have direct evidence for meteorite impacts. It could be right, but it's not the simplest explanation for the data we have. And this comes back to our conversation we had with Mike Ackerson about how science is done. And people publish things that end up being wrong. I've published stuff that ends up being wrong, and that's fine. These ideas keep getting sort of iterated around and kind of worked on. And so meteorite impacts, maybe we need to test it. I don't think there's evidence for it yet, but it's possible. Other people are searching for old rocks and, still kind of debating the age of the rocks. Some people would argue that the Acasta Gneiss complex is actually just 3.9 billion years old, that the 4 billion year old rocks are not actually 4 billion years old. They're inheriting stuff. So There's still debate.
Does that seem a bit pedantic to you?
I think it seems a bit pedantic, and I think we really kind of nailed the age. Like, I think we produced a really good age for rocks that we know are igneous, and so it's not really up for debate on that one.
The Acasta complex is 4.019 plus or minus 1.8 million years old. Because you know what? That million years, it matters.
It matters.
So,
get it right.
There we go.
It matters.
It is established because, hey, this is Jesse's podcast, everybody.
Yeah, I'm going to rename it the Acasta Gneiss podcast, actually.
No, you're going to name it the Jesse Reimink podcast with his little sidekick, Chris.
Yeah.
His old little sidekick.
You could get a little sort of Batman and Robin photo going on for the cover art. I like this idea.
Yeah,
Chris.
over my dead body.
Really
over my dead body.
Oh,
all right.
man.
So, Jesse. No, it's not good stuff, actually. I'm offended. Real quick, I think we need to move on to like where are we at now. I think we've already established this, but where are we now?
There's a lot of outstanding questions here. One of them is like, where are the 4.2 billion year old rocks? Are they still out there? We talked about the fact that there's this one xenocrystic zircon core that's 4.2 billion years old. So there must have been 4.2 billion year old rocks there. I don't know if they still are or not. It's open for debate.
So in geology, we use the kind of turn of phrase a lot of walking the contact. Is this just a matter of just stumbling upon the right outcrop, you think? Or maybe it's, you said there's a lot of water, so you only have access to a certain amount of it. Do you think it's there?
It's a great question. I don't know. There's a bunch of different colors of gray here. And the darkest ones are mafic. We don't know how to date those. It's really hard to date really metamorphosed mafic rocks.
All right. We need to tease that out just for like 30 seconds. Why are mafic rocks difficult to date?
Old ones are really difficult because they just don't have zircon in them. They didn't form zircon.
Oh, okay.
Initially.
Yeah.
It's basically as simple as that.
Are they going to be more in the lighter bands, the zircons, then, as opposed to the darker bands? Okay,
that's exactly right.
Makes sense. Okay.
So that just shows there's a lot of mafic rocks out there. Some of them might be 4.2 billion years old. We just haven't took the time to try and date them. The other complexity here is that you look at this image number 7, there's 5 different rock compositions in different ages in that one outcrop.
Where are your legs in this? I want to see your legs. You're on the left.
I'm on the top
left.
Yeah, those are my legs. Those are my big boots there. So it takes a lot. You have to date almost every rock you come across. You have to like get zircons out, date the zircons to figure out the age. And so you just can't date them all. So you kind of end up, I don't know, Chris. I don't know the answer if there is and how to find them.
I have a question then. This area has been heavily glaciated. Have you studied that? The glacial deposits.
We actually have. It's
like because they would have picked up stuff and scoured it and gotten deeper and then plopped it off.
It's a great idea, Chris. And there was a master's student at the University of Alberta who actually looked at esker zircons. Chris gets the Segway Award today because eskers are, we see some eskers in Michigan, not a lot of eskers, right? Like there's not too many eskers preserved.
There are clusters of eskers in Michigan, yes. And you get them in Minnesota a lot. So an esker it's what we call stratified drift for glaciologists. This is, it's a deposit that is formed by rivers that are running through glaciers, at the bottom of glaciers, and so on. And the river in a glacier and in the middle of a glacier and even on top of a glacier has everything that a normal river would have. It has stream banks. It has, a stream bed. It sorts the sediment in every single way because it's a water deposit. And then as the glacier melts, it all just kind of slumps together. And it forms this kind of sinuous, snake-like, meandering river deposit, essentially. And it's just kind of plopped off on top of the land. And so they're really, really cool.
They're totally cool.
If they are very cool. Like Jesse, to me, there's nothing better than going for a long run on top of an esker. It's spectacular. They make great roads because these backcountry roads, because they're gravel, essentially sand and gravel, and they have great drainage. So if you just, make a dirt path on top of it, they're awesome for that, for dirt roads.
You're hitting all the key points here, and they stand out like a sore thumb. And you got to think back to the Laurentide ice sheet. The entire region was covered by an ice sheet, and this ice sheet was retreating. And eskers in this region are spaced every 10 kilometers. You'll have a big esker sort of train, a big esker system. And they're running kind of, in this part of the world, they're running from east to west, kind of from where the center of the Laurentide ice sheet was out to the west is where they're draining. So we looked at zircons.
Yeah, that's interesting too, Jesse, because most of the eskers we have in Michigan would run north-south.
Yeah, exactly. So in this part of the Northwest Territories, it was the ice sheet center was due east, basically.
So basically what that means, everybody, is that the eskers are going to run parallel to the motion of the leading edge of the glacier. And these kinds of ice sheets are so massive that they spread outward from the zone of accumulation. So wherever the ice was the thickest, they would just kind of ooze outward in all directions.
And the beauty about eskers, because you have a bunch of glacial sediments. You have till, reworked material that is different glaciers.
Unsorted, unstratified, on everything. Yeah.
Whereas and till can be sourced from hundreds of miles away because it's picked up in the ice and then dumped off. Eskers, the thought is, and there's a bunch of people who've worked on, mostly in the diamond community, like people used eskers to trace diamond deposits down. Eskers they sample rocks 5 kilometers by 5 kilometers upstream from your sample site, or maybe 10 by 10 or something like that. They're a little bit more localized sort of sampling devices. And so we sampled the eskers and looked at the zircons in the eskers and in some way kind of mapped out where old rocks are in Acasta. And basically the story is there's not a lot of 4.0 billion year old rocks out there. There's a decent amount of 3.7 and there's a bunch of 3.4 billion year old rocks in the Acasta Gneiss complex. So the 4 billion year old stuff looks to be fairly restricted. We didn't see a lot of 4 billion year old zircons in the esker zircons. Let's put it that way.
Okay. So basically that's really interesting. Actually, you're saying that if you look at the ratio of the age of the zircons that you find in there, it's going to give you a pretty good summary of the ages of the rocks that are exposed in the craton in the Northwest Territories where the Acasta is formed. That's interesting. That makes a lot of sense, but I never really thought about it before. So,
yeah, so
okay.
they're actually they're not perfect, but they're decent sort of samplers in that regard. So the other thing.
So how big of an area are we talking about then in terms of like where this Acasta complex is? Like what are we referring to?
So where everybody has studied, basically everybody studied about including myself, a dozen PhD projects in an area that's about 30 to 50 square kilometers. The Acasta Gneiss complex is more like 1,300 square kilometers, and most of that's pretty unstudied, apart from sort of this esker sampling thing we did. But there's a ton of gneisses that are exposed that nobody's dated. And actually a master's student of mine, we're about to publish this work, but a master's student about 250 kilometers north, almost on the Arctic coast, image number 9 shows the location of this. She found some samples that are 3.8 billion year old samples, and they look just like Acasta. And so there might be a bunch of old crust in this area that we just don't know about outside of this little 30 square kilometer window that everybody's studied. It's just really hard to explore. So yeah, so that's sort of an open question, is like, are there more old rocks? How extensive are they? We just don't really know.
Really interesting. Probably a bigger area than it's so hard to get to. This is so remote,
yeah.
Which leads me to the last thing that I want to talk about actually is, all right, the Acastanite is pretty damn awesome. It's very difficult to get to. So first of all, one, is it getting mined at all for anything? And two, how do people get their hands on a piece of Acasta? Because I have mine. You have yours.
You have yours from, that's exactly right. I have mine. So yeah, there are people at least 2 who have staked mineral claims on the Acasta Gneiss complex to extract.
What are they looking for?
They're just getting rocks to sell. And so that answers the second question. Really, that's what they're doing. They're getting They'll make necklaces out of it. They'll make little bookends. They'll make coasters. They'll just sell raw slabs of it. And if you go to like whatever, eBay or whatever you're buying things on, you'll find probably Acasta Gneiss complex samples. And, at the gem and mineral shows, there'll probably be somebody selling them. So they get passed around. I've met a couple of these people who have these
I was going to say, are they reliable?
The super nice, the one guy I've met, super nice guy, has this mining claim, and he's really interested in understanding the sort of chronology, because we've shown a bunch of images of how complicated these outcrops are. So you can't just rock up to an outcrop and take a sample and say it would be accurate to say this is the Acasta Gneiss, but it's inaccurate to say this is a 4 billion year old rock, because in one outcrop there's 5 different ages of rocks. So
is mine a 4 billion year old rock?
Yours is definitively a 4 billion year old rock. I can show you the publication.
All right.
But I would just say be a little careful. It's really hard to tell. You just can't really tell unless you like dated the individual sample, brought it to my lab, and like we measured the ages. It's just really hard to tell if that is actually the oldest rock in the world, or if it's the piece right next to it that's actually 3.6 billion years old or 3.8 billion years old. And so part of it doesn't matter because it's from up there. Like part of it doesn't really matter.
It doesn't matter. I mean, I'm happy that I have a 4 billion year old rock. Do I have a 4.02 billion year old rock?
You have a 4.02 billion.
See, I love that.
But
you
Chris,
know what?
It wouldn't, if you had
I'd be pretty damn happy if I had a 3.4 billion year old rock.
If you had a 3.6 billion year old rock, you would still have one of the 6 oldest rocks in the face of the earth that we know of. So like, is it really that big of a difference? I mean, I don't know if it matters.
And I'm going to say too that it is an absolutely gorgeous rock. Jesse, you and I love this. We love the look of these tortured rocks. My countertops they're intensely metamorphic, and I couldn't go with anything else.
It's the deep roots of the continents, man. It's like so good. The deep tortured roots.
Absolutely.
It's like, going to the Grand Canyon, and you got to see the deep stuff at the base of it, man. It's like the best.
You have to see the Vishnu.
To the Vishnu. Those were shirts we had. That was what our shirts said when on the field
awesome.
camp I went to. It was to the Vishnu.
I mean, hey, so erosion happens.
Erosion happens, baby. Okay, Chris, that's the spiel about the Acasta Gneiss. That's the end of part 2 of the spiel.
Absolutely. Cheers.
Peace.